A small spacecraft is moving farther from the Sun than any planet. It carries one optical telescope and has one single job: to sit on a specific line in deep space and look back toward the Sun. From that position, the Sun is no longer simply a star, it is acting as a gravitational lens. Light from a distant world has been bent around the Sun's mass and concentrated into a faint ring of light around the solar disk. That ring is the optical fingerprint of a planet tens of trillions of miles away. This is not a metaphor. The Sun really can be used as a lens. Sustained work from a small group of researchers at JPL has treated the idea seriously enough to publish detailed imaging proposals around it. The optics are real, the amplification is enormous, the angular reach is fine enough to discuss alongside the imaging of an Earth-sized planet around another star. But for this to work, the spacecraft must position the optical telescope in a region of the outer solar system where current missions have barely been. The geometry that makes the lens useful begins around 550 astronomical units. That is more than 50 billion miles from the Sun, and the more recent mission work centers the practical observing band farther out, closer to 650 to 900 astronomical units, roughly 60 to 84 billion miles away. By the end of tonight, you will understand what it would take to turn the Sun into the largest working telescope we have ever used, and why making it work would mean solving some of the hardest problems in navigation, engineering, and measurement. If you enjoy exploring questions like this with me, subscribing to the channel helps others find them too. Liking and sharing the video helps even more. Let's begin. A gravitational lens is not a piece of glass, it is a path. When light from a distant source passes near a massive object, the gravity of that object bends the path the light is following. The light continues to travel in a straight line as far as the light is concerned. The space it travels through is no longer flat. On the far side of the massive object, paths that started out spread apart can be pushed back together. That convergence is what a telescope mirror would normally do with shape and silver. A massive enough body can do the same job with no glass at all. For the Sun, the bending is extremely small. Light grazing the solar limb is deflected by about 1.75 arcseconds, the same number measured during the 1919 eclipse expedition. That number is not impressive on its own. What matters is what happens when the deflected light is allowed to keep traveling. The bent rays converge along a focal region that begins far beyond Neptune. Inside that region, light from a distant source can pile up by an enormous factor. The 2018 paper from Slava Turishev and colleagues at the Jet Propulsion Laboratory gives the numbers. At a wavelength near 1 micrometer, close to the brightness peak of a Sun-like or Earth-like target, the amplification provided by the solar gravitational lens is around 10 to the 11th. That is roughly 100 billion. The angular resolution discussed for the same configuration is around 10 to the minus 10 arcseconds. That is something like 10 orders of magnitude finer than the best existing space telescopes. Those two numbers are why the idea has not been quietly abandoned. With anything close to that amplification, even a small instrument receives enough light from a distant planet to do real imaging work. With anything close to that angular resolution, the same instrument can in principle separate features on that planet at scales much smaller than the planet itself. No conventional aperture small enough to launch and operate can offer this combination through its own optics alone. The Sun supplies what the aperture cannot. This is not loose enthusiasm. It is an optical claim grounded in general relativity, made on the basis of how much light can be collected and how much it is bent on the way. The 2018 paper is one of several. The same author and a small group of collaborators have continued to publish through 2020, 2022, 2025, and 2026. Building on the original treatment with mission concepts, imaging analysis, propulsion trades, and observability benchmarks. Together they form a sustained research lane around a single physical claim. The Sun is the only natural optical aperture in this solar system, with the gain and resolution needed to consider resolved imaging of an Earth-like exoplanet at all. So the answer to whether the Sun could become a telescope, in a strict optical sense, is already yes. A planet around another star can be made to deposit enough light onto a small detector to be measured. The geometry that does this is fixed by physics not by the size of the spacecraft. What remains to ask, before anything else, is where exactly the detector has to be sitting when that light arrives. It helps to set this resolution claim against the resolution of an ordinary telescope. The James Webb Space Telescope has a primary mirror about 6.5 meters across. At infrared wavelengths, it reaches an angular resolution of around 0.1 arcseconds. That is good enough to see the disk of Jupiter from Earth. It is nowhere near good enough to see the disk of an Earth-sized planet 30 parsecs away. To even begin to resolve the surface of such a world directly, an optical system would need an angular resolution about 1 billion times sharper than Webb. A conventional approach to that problem is to build a much larger aperture in space, or to build an interferometer that spans hundreds or thousands of kilometers and synthesizes a single effective aperture from many separated mirrors. Both routes have been studied. Both are at least one and probably several generations away from delivering resolved imaging of an Earth analog. The supply-side problem is brutal. Building, launching, deploying, and stabilizing a kilometer-scale optical instrument is its own field of slow and expensive engineering. The 2020 follow-up paper from Turishev and collaborators describes how a small telescope could in principle bypass this size race. A 1-meter aperture, sitting in the right place in the focal region of the solar gravitational lens, is treated as a serious imaging instrument for an Earth-like exoplanet. The mirror is small. The work is done by the lens, which is the Sun. The instrument behind the lens is collecting light that has already been amplified by a factor of 10 to the 11th, with angular detail set by the geometry of the bend rather than by the diameter of any glass that humans had to lift off the ground. That is why the proposal stays in serious discussion. It is not a small improvement on Webb. It is a different way of using the Sun. Instead of trying to make the aperture bigger, the aperture becomes the Sun itself, with a small spacecraft acting as the focal plane detector. None of this implies that the rest of the problem is finished. A 1-meter telescope is a real piece of hardware only if it is in the right place, pointed the right way, and able to operate for the time the science requires. The optical claim says nothing about how to get the spacecraft to that position, how to maintain it there, or how to bring the data back to Earth. Those are not minor footnotes. They are separate physical and engineering problems with their own constraints, and they have to be answered separately. So this is the first reversal. The optical claim is strong, specific, and continuous in the literature. It survives ordinary scrutiny about resolution and photon budget. It justifies treating the Sun as a real candidate lens for an Earth-like exoplanet, with a small spacecraft as its companion detector. What it does not do, and what it cannot do on its own, is fix the question of where the spacecraft has to be. That is the next question, and it sets the geometry for everything that follows. It is worth pausing on one more piece of context before moving on. The same gravitational bending that the SGL exploits was first measured during a solar eclipse expedition in 1919, when Arthur Eddington and his colleagues observed the apparent positions of stars near the eclipsed Sun. The measured deflection of those stars matched the prediction of general relativity around 1.75 arcseconds at the solar limb. That measurement is more than 100 years old. It has been confirmed many times by radio interferometry and by spacecraft tracking experiments with steadily smaller error bars. The optical effect underlying the SGL is one of the most thoroughly tested predictions in modern physics. Whatever else is uncertain about the mission proposal, the basic bending of light by the Sun is not. So the question of whether the Sun is a real lens has in some sense been settled for a century. The question of whether the resulting focal region can be used as an imaging instrument is much newer, and it is the question the more recent SGL papers are working through. The 2018 paper put the resolution and amplification numbers in front of the field. The 2020 paper attached a concrete mission concept. The 2022 paper worked through the resolved imaging problem. The 2025 paper compared the SGL against the rest of the direct imaging landscape. The 2026 paper added the observability benchmark and the propulsion trades analysis. 5 papers spread across 8 years by overlapping author lists, building on each other. That is what a sustained research lane looks like. 550 astronomical units sounds like an address. It is not. It is a doorway. 1 astronomical unit is the average distance from Earth to the Sun. Neptune orbits at about 30 AU. Pluto is around 39 AU on average. The heliopause, where the solar wind merges with the interstellar medium, sits somewhere near 120 AU. The closest stars are out at roughly 270,000 AU. On that scale, 550 AU is far beyond the planets, far beyond the edge of the heliosphere, and still a tiny fraction of the way to anywhere else. That number is set by the geometry of the bend. Light from a distant point source, after grazing the limb of the Sun, comes back into a converging cone with its tip somewhere out near 550 AU. Closer in than that, the bent rays have not yet crossed. Outside it, the rays continue to overlap and the lens stays useful. So the geometric focal region begins beyond about 550 AU and extends outward, in principle without a sharp far edge. That word, region, matters more than the single number. The solar gravitational lens does not put its image in a point. It puts it in an extended region along a line. A spacecraft can sit somewhere along that line and see the lensed light. Move outward along the line by a few AU and the spacecraft still sees a useful lensed image, with the geometry slightly changed. Move sideways off the line by a meter and the image of the planet rotates, distorts, or disappears. The lens is line-shaped, not point-shaped. It helps to picture the geometry physically. The Sun is a body about 1.4 million kilometers across. Light from a distant point source passes near its limb and is bent by a small amount. On the far side, the bent rays form what mathematicians call a caustic surface. Inside the caustic, the lensing is strong, and the rays from a given source overlap into a coherent image. The inner edge of that caustic, for the Sun, lies near 550 AU. Outside it, the caustic extends along a line in the direction opposite the source, with no sharp far boundary. A spacecraft that sits on or near that line, at any distance beyond about 550 AU, can in principle observe the lensed signal of the source. This matters because it removes a tempting picture. It is easy to imagine a focal region as a particular point in space, like a Lagrange point, where a spacecraft parks and starts collecting an image. The solar gravitational lens does not work like that. The threshold at 550 AU is the inner end of an extended line whose useful length depends on the target. A spacecraft does not arrive at the focus and stop. It enters the focal region and then has to keep going, scanning along the line where the image actually lives. So 550 AU is best treated as the point at which the lens begins to do anything optical at all. It is not the point at which observations become operationally easy, and it is not the point at which a mission can claim that it has reached its science zone. Those questions belong farther out, where the geometry, the lighting, and the mission profile all align more usefully. This is where the public number and the working number begin to separate. The 550 AU figure shows up in the value paper and gets quoted as the threshold of the focal region, because that is what it is. The mission design papers do not center their analyses there. The 2026 Propulsion Trades paper from Turyshev frames mission-useful work around 650 AU, with discussion extending out toward 900 AU as a more comfortable practical band. The 2025 comparison paper uses the same kind of range when it sets up the SGL as one of several possible paths to resolved imaging of an Earth analog. The reason for that shift is partly optical and partly operational. Slightly farther out along the focal line, the image plane geometry is more forgiving. The Einstein ring is cleaner. The signal contrast against the corona is better. The lensed image is wider in the spacecraft's reference, which gives more room to scan across it. The mission concept also gets simpler if the spacecraft is far enough out that the geometry is not changing too rapidly with small position errors. But every extra AU of distance carries its own cost. At 650 AU, the round-trip light time grows to roughly 7.5 days. A small command sent from Earth would take about 90 hours to arrive, with a reply of similar length on the way back. Solar electrical power has long since become impractical at those distances. Onboard power has to come from radioisotope sources or from a small nuclear reactor. The communication links are operating at extreme distances, so data rates are low. Each scientific instrument has to live longer and consume less than would be typical near Earth. So the practical observing zone is described as something like 650 to 900 AU rather than 550 to 600, because that is where the optics, the mission geometry, and the operating environment all give something usable at the same time. It is a band, not a point, and even inside it the spacecraft is not standing still. The whole arrangement is built around an outbound line that the spacecraft has to follow for years after it crosses the threshold at 550. It is also worth noting what 650 AU looks like from inside the solar system. Light from the Sun reaches Earth in about 8 minutes. Light reaches Jupiter in around 40 minutes, and Neptune in around 4 hours. By the time light reaches 650 AU, it has been traveling for about 90 hours, or close to 4 days. The spacecraft would be roughly 21 times farther from the Sun than Neptune, and around 4 times farther than the Voyager 1 spacecraft is right now. That distance is not in the same league as interstellar space, where the nearest stars are out at hundreds of thousands of AU. It is also nowhere close to a place from which Earth could exercise the kind of moment-to-moment control that current planetary missions enjoy. The other reason for working out to 650 AU, rather than starting at 550, has to do with the structure of the lensed image. The 2022 Resolved Imaging paper and the 2026 Observability paper both treat the relationship between distance along the focal line and the size of the projected image plane. Closer to 550 AU, the image plane is narrower, the geometry is more sensitive to small alignment errors, and the recovery is harder. Farther out, the projection of the target onto the spacecraft's image plane is wider, the sample pitch is more relaxed, and the alignment tolerance is somewhat easier. The trade is more cruise time for a more forgiving observing configuration. The mission planners take that trade because the operational margin matters more than the additional years of transfer. This rearranges the question. Asking whether the Sun can become a telescope at this point is no longer mainly a question about gravity and light. It is a question about a long line through deep space that the spacecraft has to occupy, that the lens has to keep cooperating with, and that the mission has to keep operating along, for as long as the science is being collected. The focal region of the solar gravitational lens is not an accessible observatory site in the ordinary sense. There is no servicing visit at 650 AU. There is no later detector swap if the first instrument is too weak. Whatever is sent has to do its work in one extended campaign, with no follow-up crew, and no nearby repair option. That is why the distance is not background scale. It decides how cautious the mission design has to be before launch. Most telescopes can be turned. A ground-based observatory rolls and pitches and follows an object across the sky. A space telescope rotates its body so a different patch of sky lands on its detectors. In both cases, the geometry is local. The optics are right next to the detectors, and the target is anywhere the system can point. The solar gravitational lens does not work that way. The lens is the entire Sun. A spacecraft trying to use it as an imaging instrument is not next to the lens at all. It is on the far side of the Sun from whatever star system it is observing. That side is not a generic location. It is a specific direction defined by the line that runs from the target star through the center of the Sun and continues outward into deep space. For any single target, that line is fixed. A planet around Proxima Centauri has one line going out behind the Sun. A planet around Tau Ceti has another. A planet around TRAPPIST-1 has a third. The Sun is still the lens in every case. The spacecraft is not. To use the Sun as a lens for a particular target, a particular spacecraft has to be on that particular line, several hundred AU out. So the observing geometry is target-specific in a way that an ordinary telescope's geometry is not. Repointing is not a small action that adjusts gimbals and reorients a mirror. Repointing means moving the spacecraft itself by some non-trivial amount to a different deep space corridor. The 2020 mission paper and the 2022 Resolved Imaging paper both treat this constraint as part of the basic mission shape. The 2018 Value paper assumes the same constraint implicitly when it sets up the geometry. This is the first sense in which the proposal stops looking like a normal telescope and starts looking like a deep space mission with optical work attached. The lens is everywhere. The useful detector position is restricted to a narrow corridor outside Neptune. The spacecraft does not choose what to look at by tilting. It chose by where it was launched, by what trajectory it follows, and by what alignment it can maintain when it gets there. Now picture the spacecraft drifting slightly off that corridor. Picture it moving sideways by a few meters. The sun has not moved, the target star has not moved, the geometry of the bend has not changed. What has changed is which rays of light from the target end up reaching the spacecraft and how those rays add up at the detector. The 2022 paper from Turyshev and Toth, which works through resolved imaging in some detail, takes this seriously. The Einstein ring of a distant planet is not infinitely thick. The image plane structure that the spacecraft is sampling has a measurable width in the direction along the line and a measurable size across it. Small offline motions do not just shift the image, they distort it. They smear out the relationship between a particular point on the planet and a particular position on the spacecraft's detector. The 2026 observability benchmark adds the same point in different language, treating image plane metrology and navigation error as dominant requirements for the mission, so the line is not a soft preference. It is part of the optics. A spacecraft that is roughly on the line gets a roughly correct image of an Einstein ring sitting around the sun. A spacecraft that knows exactly where it is on the line and exactly how far off it is from the ideal corridor can interpret the ring properly when the data is reduced later. A spacecraft that does not know its position to sufficient precision degrades the eventual image even if its detector is performing perfectly. This is what makes the spacecraft's flight different from anything in current deep space practice. Voyager 1 is now more than 160 AU out. Its scientific instruments measure fields and particles. Its position errors do not corrupt the data because the data is not an image of a specific point in space. A solar gravitational lens mission cannot afford that style of loose navigation. The data, by construction, depends on the geometry that the spacecraft is asserting. There is a useful comparison with radio interferometry. An array like the Very Long Baseline Array uses widely separated radio dishes to synthesize a large effective aperture. The system's resolution depends on the precise geometry of the array. Each dish has to know its position relative to the others to a small fraction of the observing wavelength. A solar gravitational lens spacecraft is in a related position, only with the sun playing the role of an enormous shared aperture and the spacecraft itself acting as a single moving sample on the image plane. The same precision discipline that radio astronomy applies to many fixed antennas has to be applied here to one moving instrument over years of observation. The implications for trajectory design are concrete. The spacecraft cannot just be pointed roughly outward from the inner solar system and then drift. Each maneuver during cruise has to be planned with the eventual focal line geometry in mind. Even small course corrections need to support the alignment the science requires after arrival. The 2026 Propulsion Trades paper takes this seriously when it lays out trajectory options. None of the candidate architectures treat the destination as a generic distance. Each one treats the destination as a specific corridor whose direction in three-dimensional space is set by the chosen target star. Then there is the question of what the mission does once it has finished with one target. A normal telescope can move to a new field in seconds or minutes, depending on its hardware. A telescope built on the focal line of the solar gravitational lens cannot. A different target lives on a different deep space corridor. To observe it, the spacecraft would have to leave the current corridor and reach the new one several hundred AU away from the sun, with the geometry pointing in a different direction. The current public papers do not pretend to have solved that problem. The 2020 mission paper and the 2026 Propulsion Trades paper treat the first target as the dominant mission shape. A separate target is not described as a quick repoint. It is treated as a structurally different mission. There are concept-level discussions of distributed spacecraft, of slow heliocentric drifts that could touch more than one corridor over very long periods, and of mission architectures designed around small candidate sets, but none of them turn an SGL spacecraft into a general-purpose observatory. A useful comparison is the cost of a corridor change. Reaching 650 AU from Earth takes a transfer that itself uses years of mission time and the bulk of the spacecraft's available delta V. To move from one outbound corridor to another corridor pointing in a different direction in 3 dimensions requires comparable delta V, even though the spacecraft would be starting from already far from the sun and ending up at another already far from the sun position. The geometry does not forgive that kind of move. Propellant that was spent on outbound speed has to be replaced by propellant for cross-track motion, and the second journey takes as long as the first if it is to be carried out under the same kind of architecture. So the practical view is bounded. A first solar gravitational lens mission is going to be a few targets at most, and very probably one chosen long before launch on the basis of what the geometry can deliver. The choice is part of the design rather than a downstream operational decision. That has consequences for what counts as the data the mission can produce, and it has to be kept in view alongside the optical claims, because no matter how powerful the lens turns out to be, what comes back depends on which corridor the spacecraft has been committed to. An Einstein ring looks like a clean image. It is not. The phrase suggests a photograph wrapped around the sun. The physical object behind the phrase is much less convenient. When light from a distant planet is bent into a ring by the sun, every point of that ring contains contributions from many points on the planet at once. The light from one continent does not land on one side of the ring. The light from one cloud does not land on a clean arc. The lensing geometry mixes the spatial information of the planet around the ring in a way that depends on where on the lens the light passed and where the spacecraft is sitting on the focal line. In other words, the spacecraft's detector does not register a small picture of the planet. It registers a sample of the Einstein ring at the spacecraft's particular position in the image plane. That sample is a function of the planet's surface, the planet's geometry, the lens geometry, and the spacecraft's location. To get back to the planet itself, the mission has to combine many such samples, taken from many positions in the image plane, and invert the mixing using a mathematical model of how the light was bent. The 2020 paper from Turyshev and colleagues describes this explicitly. The 2022 paper on resolved imaging goes further into the structure of the inversion. The output in their treatment is not a single exposure that becomes a planet image after some sharpening. It is the result of a long observing campaign that samples the image plane on a grid, fits the resulting data to a model of the lens, and reconstructs an estimate of the planet at the modeled spatial scale. This changes what the word picture means. A picture, in normal usage, implies a one-to-one map between the world and the detector. Each pixel sees a small patch of sky, and only that patch. The detector then becomes a quiet record of what was in front of it. The Einstein ring of a distant planet, by contrast, is a structured optical artifact whose meaning has to be unpacked. It is closer in spirit to a radio interferogram or a holographic recording than to a snapshot. That is not a complaint about the proposal. It is the actual data product the proposal is trying to obtain. What it requires from a listener is patience with one specific change of intuition. The sun is a lens. The Einstein ring is the lensed signal. The picture, in the ordinary sense, is what comes after a great deal of careful computational work that uses many samples of that signal taken from a slowly moving spacecraft. The 2026 observability paper from Turyshev gives a useful benchmark for the size of this problem. It takes a specific target, an Earth-radius planet, orbiting at the inner edge of a Sun-like star's habitable zone, located 30 parsecs away. It places the observing spacecraft at 650 astronomical units with a 1-meter telescope. With those choices, the projected image cylinder of the planet at the spacecraft's position is about 1,338 meters across. That is roughly 1.34 kilometers. A picture of the planet at 128 by 128 pixels, which is a fairly modest image, would correspond to a raster of points on that cylinder. With the image cylinder fixed at 1.338 kilometers and the desired pixel count fixed at 128 across, the spacing between adjacent sampling positions becomes about 10.46 meters. That is the spacecraft's step size in the image plane when it scans for a 128 by 128 result. That number is small, but it is not unreasonable for a spacecraft that is moving slowly along its corridor. It is also not free. It implies that a 1-meter telescope at 650 AU has to be able to position itself to about 10 meters in the image plane sense. And it has to know its own position with enough precision that each sample can be tied back to a particular cell of the reconstruction grid. The benchmark is a modeled case rather than a final mission specification, but it sets the scale. The image plane is kilometers across. The required step is meters. The spacecraft has to step accurately, and it has to step many times. That is why a long observing campaign is part of the basic shape of the proposal. The image is not a single click of a shutter. It is the accumulation of a few thousand samples across an image plane that does not exist in any literal sense at the spacecraft's position. Each sample contributes a slice of the inversion. Each missed or misplaced sample leaves a hole or a smear in the reconstructed planet. For a resolved image, the mission has to keep scanning for as long as the modeled dataset requires. The 2020 paper and the 2022 paper both treat this as a multi-year observing program, not a single exposure. The 2026 paper supports the same picture from the noise side by working through how many samples are needed to recover the planet's signal in the presence of coronal and detector backgrounds. It is also worth understanding why the image plane is the size it is. The bend angle for light grazing the Sun's limb is about 1.75 arcseconds, an extremely small angle. At a focal distance of 650 AU, that small angle subtends a physical scale of order a kilometer at the spacecraft. The projection of a target planet through that geometry has a finite width set by the ratio of the planet's physical size to its distance from us. For an Earth radius planet at 30 parsecs, the geometric projection in the spacecraft's reference comes out to the 1,338 meters that the 2026 benchmark uses. A different target with a different size or distance would give a different cylinder width and a different required sampling pitch. The physics is the same. The numbers shift. The same geometry has another useful consequence. The image plane is a slowly varying property of the focal line. As the spacecraft moves outward along the corridor by tens of AU, the size of the image cylinder and the spacing of useful samples change gradually rather than abruptly. That gives the mission planner some flexibility about exactly where the spacecraft observes within the 650 to 900 AU band, without giving away the basic structural fact that each sample still has to be placed at a known position to a meaningful fraction of the pitch the benchmark requires. So the deeper claim that follows the ring picture is this: even with the lens performing exactly as expected, the spacecraft does not get an immediate planet image. It gets the right to begin a careful, controlled, long-duration sampling program that turns the ring's mixed information into an estimate of the planet. The optical claim and the data product are not the same claim. One is about how light is bent. The other is about how a small mission can recover what was hidden in that bend. A useful way to think about what the spacecraft is doing during a single sample is to compare it with a single pixel exposure on an ordinary camera. An ordinary camera pixel collects light from a small angular patch of sky during a short integration. The sample's meaning is direct. A solar gravitational lens sample, by contrast, collects light from the whole Einstein ring during a short integration, with the spacecraft sitting at a specific position. The sample's meaning is encoded in both the photon count and the spacecraft's position. To get to a planet, the mission has to combine many such samples, each tagged with its position, into a single self-consistent reconstruction. That bookkeeping is why the data pipeline is part of the instrument and not a separate later step. Sampling sounds like a small word for what is actually happening. The spacecraft is not sitting still while the planet's image arrives. The spacecraft is moving, slowly and deliberately, across an image plane defined by the geometry of the Sun, the target, and itself. Each measurement is taken at a slightly different position, and each new position carries new information. The motion is not arbitrary. It is set by the observing strategy. To recover a planet at some particular spatial resolution, the spacecraft has to visit a particular set of positions in the image plane with known spacing and known timing. A raster across the image cylinder of the kind the 2026 benchmark describes for a 128 by 128 reconstruction asks the spacecraft to step from one grid position to the next, settle, take its measurement, and step again. For this to produce a meaningful inversion, the step has to be repeatable. The spacecraft has to be able to move by 10 meters in a controlled direction, then move by another 10 meters along the same direction, then turn the raster and step in a new direction, all while maintaining its orientation toward the Sun and toward the lensed light. The 2020 mission paper treats this as central to the observing scheme. The 2026 benchmark adds that the image plane positions have to be known to a precision that makes each sample interpretable in the inversion. So the work of scanning is part of the work of seeing. It is not a separate operations problem outside the optics. The optics, by their nature, need samples at known positions. The motion that puts the spacecraft in those positions is part of how the planet eventually gets recovered. If a step is too long or too short, the spacecraft's sample lands in the wrong cell of the reconstruction. If the spacecraft drifts during the integration, the sample becomes a blur of several positions averaged together. If the spacecraft loses its orientation, the geometry of the inversion breaks because the lensed light is no longer hitting the detector along the assumed direction. None of these failures are dramatic individually. Cumulatively, they degrade the recovered image until it is no longer a faithful estimate of the planet. That is the first reason scanning behavior is not a quiet operations detail. It is the second reason that explains why mission design papers spend as much time on the spacecraft's motion as they do on its optics. Then there is the planet itself. The Sun's gravitational lens is fixed. The geometry of the bend does not change on the timescales of the mission. The target planet does. A world the size of Earth around a sun-like star is not a static object. Clouds form, drift, and dissipate over hours and days. The planet rotates, continents move into and out of view, volcanic activity, weather systems, and seasonal change all alter the light that the planet sends back into space. The mission has to recover an image from samples that may take months to a year or more to accumulate. The planet has done several rotations and several weather cycles in that time. The 2022 resolved imaging paper acknowledges this complication. The reconstruction has to account in some form for the planet's own time dependence. It cannot treat the body as static the way an ordinary direct image would. That does not make the problem impossible. It does mean that the inversion has more parameters and that the dataset has to be richer. Some of the planet's temporal variation is in fact useful. Rotation modulates the signal in a way that helps separate features at different longitudes. Cloud variability changes the signal in ways that can be modeled as additional layers in the recovery. The 2026 paper discusses this kind of dynamic inversion as part of the realistic problem the modeled benchmark is trying to capture. So the planet is not just a target, it is a moving, weather-active object whose own behavior during the observing campaign becomes part of the data being interpreted. That is a richer problem than imaging a fixed object, and it is one of the reasons reconstruction is treated as an open scientific question rather than a finished pipeline. There is one more aspect of the dynamic problem worth surfacing. Rotation also helps separate features at different longitudes on the planet, since the lensed signal modulates as the planet turns. A model that incorporates rotation can in principle pull out longitudinal structure that a single snapshot measurement could not. The 2022 paper points out that this kind of time-resolved analysis is part of why a long observing campaign is even informative. Without rotation modulation and without slow weather variability, the inversion has less to work from. With them, the dataset carries more information about the planet's surface than a static snapshot could. That does not make the inversion easy. It does mean the campaign's length and the planet's natural variability are doing useful work together, as long as the inversion can model both. The cost is more parameters in the recovery and a greater dependence on the assumptions feeding the model. The benefit is a richer estimate of the planet, including information about how brightness across its surface changes with rotation. Now suppose the spacecraft's motion is well controlled and the planet's variability is well modeled. There is still the question of how well the spacecraft knows where it is. The 2026 observability benchmark is quite specific about this. Image plane metrology is named as a dominant requirement. The image plane in question is roughly a kilometer across. The spacecraft is meant to step through it in increments of about 10 meters. To turn its measurements into samples that the inversion can interpret, the spacecraft has to know each sample's position to a fraction of that step. Small position errors do not just shift the planet image, they multiply through the inversion and distort it. That is unusual. Most deep space missions report their position with errors of meters to tens of meters, which is more than adequate for orbital mechanics. Position errors of a meter in deep space, while routine for navigation purposes, become a major issue when they correspond to a meaningful fraction of the spacing between image samples. The spacecraft is essentially being asked to do navigation to a precision that matters scientifically rather than only operationally. This is also why the proposal pairs the scientific instrument with metrology hardware. A laser interferometer, a precise inertial reference, or a star tracker constellation built into the spacecraft is not optional. It is part of what makes the eventual reconstruction trustworthy. The 2020 paper and the 2026 benchmark both place this kind of instrumentation in the basic design, not as a stretch goal. There is also the matter of when the metrology has to work. Position errors that occurred days ago are not directly useful to the inversion, which needs to interpret each sample as it was actually taken. Either the spacecraft has to have known its position at the moment of each sample, with onboard metrology fine enough to log it, or the data has to be tagged with enough auxiliary information that the position can be reconstructed in post-processing. Most of the published designs combine both. Real-time precision is used to keep the spacecraft on its corridor. Post-processing precision is used to interpret each sample within the inversion, so the picture so far is consistent. The lens is real, the observing line is real, the Einstein ring is real. The image plane is real in the sense that the geometry it describes is well defined. The spacecraft has to step through that image plane with careful motion, careful knowledge of its own position, and a model of how the target itself is changing during the campaign. The Sun does the optical work. The spacecraft does the disciplined sampling that turns that optical work into something a reconstruction can interpret. And all of this has to be done before the brightest object in the entire arrangement is even taken into account. The Sun is part of the instrument. It is also the brightest object in the field by an enormous margin. The same body that bends the light from a distant planet into a usable ring is sitting at the center of that ring, glowing with a corona that the spacecraft cannot turn off. In ordinary terms, the lensed Einstein ring is faint. The amplification is large in the sense that more of the planet's light has been steered toward the spacecraft than would otherwise be the case. The signal is still a very small number of photons compared with the light coming directly from the Sun's outer atmosphere. The corona stretches out for many solar radii. It has structure. It changes with the solar cycle. It is also stochastic, which means its brightness in any small region fluctuates in time as plasma moves through it. The 2022 resolved imaging paper by Turyshev and Toth identifies the corona as the main stochastic noise source for the observing problem. The 2020 mission paper makes the same assumption when it sets up its noise budget. Coronal brightness in this picture is not a background that can be averaged away. It is a noise source that has to be modeled, calibrated, and subtracted before the planetary signal can be cleanly recovered. That changes the easy intuition. A stronger lens does not automatically mean an easier measurement. The same Sun that makes the lens possible is the thing the spacecraft has to look past. It is not analogous to a telescope mirror that quietly sits behind the detector. It is closer to a very bright lamp that the experiment cannot remove from the field of view. So the answer to whether a more powerful lens makes imaging cleaner has a built-in caveat. The lens itself is powerful, but it lives inside its own glare. The mission has to spend some of its design effort on dealing with the source of the glare, even though that source is also the reason the proposal exists at all. A coronagraph is the standard response. The idea is straightforward in principle. A small occulting mask placed in front of the detector blocks the bright disk of the Sun and lets the spacecraft see structures very close to the limb, like the Einstein ring of the lensed planet. Coronagraphs are common on solar telescopes and have been used in space for decades. The 2018 and 2020 papers both assume a coronagraph as part of the instrument. A coronagraph helps. It does not solve the problem. The corona is not the same thing as the bright photosphere. It is the diffused, structured outer atmosphere of the Sun, and it extends well past the region a coronagraph mask can block. Even with the disk hidden, the spacecraft is still looking through the corona and at the ring of light that the lens has shaped. The corona contributes both a slowly varying background and a fluctuating noise pattern that the measurement has to live with. So the coronagraph's job is partial. It cuts down the direct glare from the Sun's surface and makes the local environment dim enough that a sensitive detector can record the Einstein ring at all. It does not eliminate a structured background. That background has to be modeled, calibrated, and subtracted in the data reduction. which means the science instrument is bundled with calibration hardware and calibration time as part of normal operations. The 2026 observability benchmark takes this further. It treats coronal calibration, ring extraction, and detector calibration as coupled problems rather than independent ones. The same dataset that carries the lensed planetary signal also carries information about the local corona, the instrument response, and any drifts the detector has accumulated. Separating those contributions in a way that does not bias the eventual planet image is part of what the reconstruction has to do. So the coronagraph is a real tool used in a real way, but its presence does not let the mission stop thinking about the sun. It changes the spacecraft's exposure to the sun's worst light. It does not erase the need for careful coronal modeling. That careful modeling is treated as part of the basic operating cost in the current literature. Now bring the two halves together. The mission has a faint Einstein ring carrying planetary information. It has a structured solar corona providing the dominant noise. It has a coronagraph that reduces direct glare but leaves the corona itself in the data. It has a long observing campaign in which both the signal and the noise will be measured repeatedly. The reconstruction problem at this point is no longer just about inverting the lens. It is about separating a small lensed signal from a larger, structured, time-varying background, while the spacecraft itself is moving through the image plane and the planet itself is changing on its own. That is the actual computational task. It is harder than simply estimating a planet from clean ring data, because some of the contrast that defines the planet only exists after the coronal contribution is correctly removed. The 2022 paper treats this as a central constraint on the eventual data quality. The 2026 benchmark treats it as a dominant requirement on the noise side of the recovery, with explicit attention to coronal residuals, ring extraction, and what the inversion has to do to handle them. None of these descriptions rule out the recovery of a planet image. They do warn that the recovery is conditional on the noise side of the problem being treated as carefully as the signal side. So the sun is doing two contradictory jobs at once. As a lens, it is supplying enormous optical gain. As a glowing star with a structured corona, it is supplying the dominant noise. Both effects are unavoidable because both come from the same body. The mission only becomes a working telescope if it can handle both at once, in the same data, in the same campaign, with the same spacecraft. A practical consequence is that the corona model the mission carries is itself a research product. Coronal physics is its own field, with decades of observations from missions like SOHO, the Solar Dynamics Observatory, and the Parker Solar Probe. Those observations provide statistical knowledge of how the corona behaves over the solar cycle, what its small-scale structure looks like, and how it varies with position around the sun. An SGL mission would build on that work to construct a baseline model of the local coronal background it expects at any given pointing. Differences between that model and the actual data would then be treated as either real planetary signal or as model error to be calibrated. This coupling is one reason the 2022 paper insists on treating the corona as a noise source rather than a removable foreground. A foreground is something that can be ignored once it is identified. A noise source remains in the data even after its mean has been subtracted. The corona behaves more like the second category. Its fluctuations are part of what the reconstruction has to model around, not something the mission can dial out. One additional complication is that the corona itself varies over the solar cycle. The solar cycle, roughly 11 years, modulates coronal brightness, structure, and small-scale activity. A mission whose observing campaign stretches across several years will see the corona change underneath it. The reconstruction has to either average across that variation or model it as another time-dependent input. The 2022 paper notes this complication. The 2026 benchmark does not assume the corona is static during the observing campaign, even though it uses a simplified coronal model for its main result. There is also a wavelength choice involved. The amplification numbers in the 2018 paper apply near 1 micrometer in the near-infrared, where the solar corona is somewhat less aggressive than in visible light, and where a typical Earth-like target's reflected light is still strong. A mission that observed in a different band would face a different signal-to-noise trade. The choice of 1 micrometer is partly an optical convenience and partly a noise budget decision. It is held across the 2020, 2022, and 2026 papers as a working assumption rather than a hard constraint. A reconstruction is not a developing photograph. There is no point at which raw data quietly resolves into a planet because enough seconds have passed. Every detail of the eventual image is the output of a calculation. That calculation takes the spacecraft's sampled ring data, a model of the lens, a model of the corona, a model of the spacecraft's positions, and a model of what kind of planet might have produced the observed signal. It then produces an estimate of the planet that is consistent with all of those inputs. The 2020 mission paper from Turyshev and colleagues treats this as the core data analysis task. The 2022 resolved imaging paper goes into the structure of the inversion. Both describe the result as conditional on the assumptions feeding the calculation. A different choice of lens model, a different treatment of the corona, or a different set of priors about the planet can in principle yield a slightly different image from the same data. That is not a failure of the method. It is how all inverse problems work. It does mean the recovered image cannot be read as a direct photograph the way an ordinary telescope image can. The 2026 observability benchmark from Turyshev makes this concrete. For an Earth radius planet at 30 parsecs, viewed from 650 AU with a 1-meter telescope, the modeled reconstruction of a 128 by 128 image is achievable under a stated set of assumptions about coronal background, detector noise, navigation precision, and observing time. The paper is careful about what that result means. It is a benchmark, not a finished demonstration. It establishes that the recovery is possible in principle for those modeled conditions. It does not assert that the same recovery will hold under the full set of real-world systematics a flown mission would encounter. That caution is part of the responsible reading of the result. The benchmark is strong evidence that the inversion is mathematically tractable and that the modeled signal-to-noise budget closes for a useful image. It is not the same as evidence that the same image will fall out of real data without further work. The kinds of effects that can intrude include time-varying coronal structures that are harder to model than the assumed background, calibration drifts in the detector over long observing campaigns, dynamic atmospheric features on the planet that the static benchmark does not include, and operator effects in the inversion where the model assumed by the recovery differs from the system that produced the data. None of these effects make the proposal unworkable. They do change how confident anyone can be about a particular reconstructed image. A modeled benchmark gives a target. A real campaign will have to demonstrate that the modeled assumptions are met, or that the inversion is robust enough to handle the actual departures. Until then, the strongest honest description is that the imaging case is supported by detailed modeled studies and remains conditional on operational confirmation. So the reconstruction sits in a specific epistemic position. It is not speculative. It rests on continuous published work, including specific numerical benchmarks, and it traces back to the same physics that motivates the optical claim. It is also not closed. There is no published end-to-end demonstration of a recovered planet image from a real lensed observation. The benchmark cases are simulation studies in which both the data and the inversion live in the same model. This separation matters more than it might sound. A picture is the kind of object that ordinary intuition treats as either there or not there. A reconstruction is the kind of object that is more or less faithful, more or less sensitive to assumptions, and more or less informative depending on how the data was taken. The proposal, taken seriously, is asking for a high-quality reconstruction rather than a single decisive image. That is a different kind of result, and it asks a different kind of confidence from anyone reading the headline. It also has practical implications for how a successful mission would be evaluated. There would be no single moment at which a planet image is unveiled. There would be a long process in which the recovered estimate is refined, the calibration models are tightened, the assumptions are stress-tested, and the inversion is rerun as the campaign progresses. Some features of the recovered image would be defensible early. Others would have to wait for enough data and enough modeling to support the claim. The output is more like a slowly improving estimate than a single photograph that arrives one day. That style of result is familiar in modern astronomy. The first images of supermassive black holes from the Event Horizon Telescope were the output of multi-year campaigns of observation and computation, with results refined as the calibration and inversion matured. The recovered black hole images were not photographs in the ordinary sense. They were reconstructions derived from an interferometric array with assumptions about source structure, atmospheric noise, and instrument response. They were still real results. The same kind of intellectual posture applies to the solar gravitational lens proposal. The output is real, and it is reconstructed. A second useful analog is medical computed tomography. A CT scan does not directly photograph a slice through a body. It takes many X-ray projections from many angles and uses an inversion to compute the underlying density distribution. The output is a reconstructed image whose quality depends on the number of projections, the precision of the geometry, the noise in each projection, and the prior assumptions the inversion uses. The same image, taken with fewer projections or a different inversion, would look slightly different. Nobody describes that as a problem. It is simply how the technology works. The solar gravitational lens proposal is closer to that mode of imaging than to a conventional camera, and its data products should be evaluated on the same terms. The third analog is the recovery of weak gravitational lensing signals in cosmology. Weak lensing surveys measure tiny distortions in the shapes of millions of background galaxies caused by the gravitational influence of intervening dark matter. The signal in any one galaxy is well below the noise. The recovered maps of dark matter distribution are statistical inversions of the combined dataset, and they depend on assumptions about galaxy shape distributions, instrument optics, and intervening systematics. They are still science, and they have produced real constraints on cosmological parameters. The solar gravitational lens proposal asks for less in some respects, because the geometry is fully specified, but it asks for similar discipline in how the data is interpreted and how the assumptions are tracked. So the second part of the optical answer is now in place. The sun can act as a lens. A small spacecraft on the focal line can sample the lensed signal. A long observing campaign can collect enough samples to support an inversion. A modeled benchmark suggests that the inversion can recover a useful image for the kind of target the proposal cares about. None of this is fantasy. All of it is conditional on assumptions that have to be met during real operations. The image, when it comes, is earned by the calculation, not handed over by the optics. That is the honest picture of what reconstruction is, and it shapes how the rest of the case for the mission has to be made. There is a fair question to ask at this point. If the proposal is this constrained, why is it on any serious list of future telescope concepts? The answer is not romance, it is comparison. The available alternatives, when they are honestly described, are not currently better. A direct image of an Earth-sized planet around a Sun-like star at a few parsecs is at the limit of what conventional space telescope concepts can do. The contrast ratio between such a planet and its star is roughly 10 to the 10th in visible light. The angular separation between the planet and the star, seen from Earth, is a small fraction of an arcsecond. To even produce a clean single-pixel detection of the planet, an instrument has to suppress its host star by 10 orders of magnitude and resolve it from the star by milliarcseconds. To produce a resolved image, in which the planet appears as more than one pixel, the same instrument has to provide hundreds to thousands of times better angular resolution than that. Current and near-term direct imaging missions are aimed at the first part of that problem. The Habitable Worlds Observatory, recommended by the most recent US decadal survey, is conceived as a roughly 6 to 8 meter space telescope with an internal coronagraph designed for habitable zone detection of Earth-sized planets around nearby Sun-like stars. The instrument is a large project. Its goal, with great care, is single-pixel detection and spectroscopy of a small number of nearby Earth analogues, not resolved imaging. Earlier concepts, such as LUVOIR and HABEX, made similar trade-offs. The 2025 comparison paper from Turishev describes this landscape and the gap between detection and resolved imaging in some detail. The supply-side problem for resolved imaging is hard for reasons that do not go away with effort. Resolution scales inversely with aperture. To resolve an Earth-sized planet at 30 parsecs at, say, 100 by 100 spatial resolution in optical wavelengths, an instrument needs an effective aperture of order 100 kilometers. A monolithic mirror at that scale is not buildable. An interferometric array at that scale is a long-term concept rather than a near-term project. Even the most ambitious published architectures, such as stellar imager class designs, push the boundary at high cost and over long schedules. This is the gap the solar gravitational lens fills, at least on paper. The 2018 paper sets up the optical case. The 2025 comparison paper organizes it relative to the alternatives. The argument is not that the SGL is a comfortable choice. The argument is that, for resolved imaging of an Earth-like planet at the spatial detail that an SGL benchmark suggests, no other available concept is close. The conventional path may eventually arrive there. The conventional path is not arriving there soon. That comparison is the only reason the route is taken seriously. If a simpler instrument could already deliver the same data product, the SGL would be a curiosity. As long as no simpler instrument can, the proposal stays on the table. It is worth being precise about what the comparison is and is not. The SGL is not better than near-term direct imaging at finding Earth-like planets. It is far worse. A nearby Earth analog could be detected and spectroscopically characterized by an in-orbit coronagraphic telescope in a few years of dedicated observation. The SGL spacecraft cannot. The SGL spacecraft has to first be flown to roughly 650 AU and then operated for a long observing campaign before any imaging begins. As a tool for surveying the habitable zone, it is the wrong instrument. As a tool for taking a serious, resolved look at one or a small handful of targets that a survey instrument has already identified, it has no current competitor. So the SGL has a clearly defined role. It is not the general-purpose exoplanet imager of the next 2 decades. It is a candidate single-target deep imaging mission, justified by the fact that for resolved imaging of an Earth-like world, there is essentially no other path. That role is rational. It is also conditional on the rest of the mission case holding up. If propulsion, autonomy, and operations cannot be made to work at the relevant scale, the optical advantage stays unused and the proposal stays a paper concept. The case for trying is therefore not heroic. It is comparative. Several research groups continue to publish on the SGL because their own analyses keep concluding that the optical promise has not been matched by other proposals. The 2025 comparison paper is the most direct articulation of this argument. It does not claim that the SGL is the only future of exoplanet science. It claims that for one specific data product, resolved imaging of an Earth-like exoplanet, the SGL is the only physically clean route that current research has surfaced. It helps to be explicit about the kinds of supply-side ideas that have been studied as alternatives. Long baseline space-based interferometers like the proposed stellar imager would use a fleet of mirrors spread across kilometers, all flying in tight formation, to synthesize a single very large aperture. Hypertelescope concepts go further and propose synthesizing apertures across tens of kilometers. Externally occulted telescopes use a separate star-shade spacecraft, flown precisely between the telescope and the target star, to cancel direct starlight without the diffraction limits of an internal coronagraph. Each of these concepts has its own decades of development effort behind it. Each could in principle close some part of the imaging gap that the SGL is aimed at. None of them have closed the gap yet. The 2025 comparison paper goes through these alternatives in language a non-specialist can follow. It is careful not to dismiss any single approach. It notes that all of them face engineering schedules that put resolved imaging of an Earth analog well beyond the 2050s on optimistic timelines, with much of the difficulty in deployment, formation, flying, or sustained operations rather than in the underlying optics. The conclusion the comparison paper reaches is that the SGL fits in this landscape as one approach among several, with a specific advantage in resolution and a specific disadvantage in mission cost, and that ruling it in or out depends on which way the supply side moves over the next few decades. That is enough to make the route worth a serious mission analysis. The next question is whether that mission analysis closes when distance is treated as schedule. So far the case has been about optics. The next part has to be about how long it takes to get to a place from which the optics can be used at all. Distance is also a calendar. So far, the figure 650 AU has been treated mainly as a position. It is also a duration, and that duration sets the practical shape of the mission. A spacecraft headed to 650 AU is on what is, by any current standard, a fast outbound trajectory. Voyager 1, the human-made object now farthest from the Sun, has been traveling outward since 1977. After about 47 years, it is around 165 AU from the Sun, moving at roughly 17 kilometers per second. At that rate, it would take about another century to reach 650 AU if it could be kept on a useful trajectory. It cannot, because its course was not set to land anywhere in particular at that distance. Voyager is the calibration point for how fast deep space missions actually fly when they are designed for other tasks. A solar gravitational lens mission needs to fly several times faster than that, or it loses its scientific relevance. The 2026 Propulsion Trades paper from Turyshev frames the problem with a specific anchor. Reaching 650 AU within about 20 years requires an average radial speed of around 32.5 AU per year, which works out to roughly 154 kilometers per second. That is roughly an order of magnitude faster than Voyager 1's current cruise. It is the speed required to keep the mission inside something close to a working career, rather than a multi-generational project. So the question of whether the Sun can become a telescope quietly turns into a propulsion question. The optical claim does not care how the spacecraft got to its observing position. The mission case does. A perfectly good lens at 650 AU is useless if no realistic launcher and propulsion system can put a 1-meter telescope there within a useful schedule. That is why mission design papers treat schedule as a first-order parameter rather than a project management detail. A mission that takes 50 years to reach its first science is not impossible, but it is institutionally hard. The personnel who designed the spacecraft will be retired before any science returns. The funding agencies that approved the project will be on later cycles. The scientific question itself may have moved by the time the data starts to arrive. A 20-year transfer is already a long mission. A century-scale transfer is a different kind of commitment, and one that current institutions are not set up to sustain. The 20-year benchmark in the 2026 paper is therefore not an arbitrary target. It is set by what a science mission can reasonably promise to deliver inside a planning horizon that funders, operators, and scientists can stay attached to. The fact that this benchmark requires roughly 32.5 AU per year of average radial speed says immediately that propulsion is one of the dominant constraints on the entire concept. Now look at the speed itself. Voyager 1 near interstellar space moves at about 17 kilometers per second after a long and successful mission profile that included several gravity assists from the giant planets. Voyager 2 is similar. The Parker Solar Probe, which holds the current record for spacecraft speed, reaches close to 200 kilometers per second briefly during its perihelion passes near the Sun. But that speed is a transient peak near the closest approach to the Sun, rather than a sustained radial cruise speed away from the Sun. None of these spacecraft give the SGL mission its required cruise speed. The 2026 paper works through what kinds of architectures could plausibly deliver an average radial speed in the range of 30 to 40 AU per year, sustained over 20 years to reach 650 to 900 AU. None of the candidates are simple. None of them give the mission planner an obvious choice. All of them ask for engineering performance that is at the edge of what current research demonstrates. It is worth being careful about what these numbers mean. An average radial speed of 154 kilometers per second over 20 years does not mean the spacecraft is moving at that speed throughout. A real trajectory begins with a launcher's burn, may involve a close pass to the Sun for a strong gravitational and propulsive kick, and then settles into a long cruise phase. The 154 number is the time average that has to be achieved for the spacecraft to actually be at 650 AU 20 years after launch. Different propulsion concepts achieve that average through different trajectory shapes. They share the constraint that the average has to be high enough to make the schedule close. The honest summary at this point is therefore not that the schedule fails. It is that the schedule is the central design constraint, and that no current architecture makes it look comfortable. The propulsion menu is short, and each entry on it asks for something that current spaceflight does not routinely deliver. That is what has to be unpacked next, because the choice of propulsion in turn shapes nearly every other element of the mission. Before any propulsion architecture is named, the broader point is worth holding clearly. A telescope is normally judged on the quality of its data and on the lifetime over which it can keep collecting that data. A solar gravitational lens telescope is also judged on whether the mission that carries it can be delivered to its observing position fast enough for the science to remain meaningful inside a single planning cycle. That is unusual. It is also what turns the 650 AU number from a position into a schedule. A lens that is real but unreachable on the calendars that decide whether missions happen is a lens that does not yet become a telescope. Some historical reference points are useful here. The Pioneer 10 and 11 missions, launched in 1972 and 1973, reached the outer solar system in years to a few decades. New Horizons launched in 2006 and reached Pluto in 2015 at 35 kilometers per second, then continued outward to its 2019 Arrokoth flyby. None of these spacecraft were designed to sustain anywhere near 150 kilometers per second. They all relied on a combination of efficient launches and gravity assists from the giant planets, and they all used the geometry of those planets to gain speed during the inner solar system phase. The 2026 paper makes clear that gravity assists alone do not deliver the SGL schedule. They help, sometimes substantially, but they cannot replace the kind of dedicated propulsion architecture that an SGL mission would need. Another reference point is the proposed interstellar probe concept that several agencies have studied in the past decade. That mission would aim at a few hundred AU on a timescale of decades, with significantly more demanding propulsion than New Horizons. Even that concept, when fully worked out, has trouble closing schedules near 20 years for a destination at 650 AU. The SGL mission is in the same regime, and the same propulsion development work that would enable an interstellar probe would help here. The two concepts share infrastructure, even though they aim at different scientific goals. A solar sail is an old idea. The basic principle is straightforward. Sunlight carries momentum. A large reflective surface intercepts that momentum and uses it to accelerate a small payload. There is no need for onboard propellant. The sun does the work for as long as the sail is in useful sunlight. For ordinary missions, sails are slow. For an outbound trajectory measured against the sun, sails are most useful when the spacecraft is close to the sun, where the radiation pressure is high. That is why sail-based solar gravitational lens concepts involve a deep perihelion pass. The spacecraft is sent on a trajectory that dives in close to the sun, deploys a large sail at perihelion, and uses the radiation pressure to fling itself outward at a much higher speed than a conventional Hoffman-style transfer could provide. The 2026 Propulsion Trades paper from Turyshev describes the parameter space for this kind of architecture. To reach 650 AU within about 20 years with a sail-only approach, the design has to combine an unusually low aerial density for the sail with an unusually deep perihelion pass for the spacecraft. The numbers are not impossible, they are aggressive. They ask the sail material to weigh less per unit area than current laboratory demonstrations, and they ask the spacecraft as a whole to survive a thermal environment close enough to the sun that ordinary materials would fail. Aerial density is the key parameter. The lighter the sail per square meter, the more acceleration the same sunlight produces. Current research samples reach aerial densities in the range of a few grams per square meter. The sail concepts that close on the SGL schedule push toward fractions of a gram per square meter, possibly with carbon-based or graphene-based ultra-thin films. Whether such materials can be manufactured at the relevant scale, deployed in space without tearing, and held flat under solar pressure, is an open engineering question. The perihelion is the other half of the trade. A spacecraft that passes very close to the sun, perhaps inside a few solar radii, receives an enormous boost in radiation pressure, but also a brutal thermal load. The structure has to survive temperatures of thousands of Kelvin and protect a science payload that, eventually, has to operate in the very cold environment of the outer solar system. The Parker Solar Probe demonstrates that close perihelions are possible with the right thermal shield. A sail-based SGL mission asks for that kind of perihelion performance, while also deploying a kilometer-scale sail at the right moment. So the sail route trades one set of difficulties for another. The optical telescope itself is small. The supporting structure is large and thin. The launch is conventional. The trajectory is brutal. The mission engineering ends up dominated by sail materials and perihelion survival, rather than by deep space cruise hardware. That is the cost of using the sun as the propulsion source as well as the lens. If the sail is rejected, the next obvious option is electric propulsion driven by nuclear power. Nuclear electric propulsion, often abbreviated NEP, uses a small fission reactor on the spacecraft to generate electricity, which is then used to accelerate a propellant through an electric thruster. The thrust is small. The fuel efficiency is enormous. Over years of continuous operation, NEP can build up a large velocity change for a payload of moderate size. The 2026 paper treats NEP as a serious alternative to the sail route. It can in principle deliver a spacecraft to the outer solar system without asking for ultra-low aerial density sails or deep perihelion passes. It also has its own problems. Reaching 650 AU inside a 20-year window with NEP alone is not comfortable. The required reactor power and propellant mass push the mission toward designs that ask for sustained performance well beyond what current space-rated reactors and thrusters have demonstrated. Longer transfer windows, closer to 30 or 40 years, are easier to close, but they collide with the schedule constraint that motivated the speed target in the first place. So the NEP option relaxes some pressures while worsening others. It avoids the harshest sail and perihelion physics, but it asks the agency planning the mission to commit to a long-lived nuclear power source operating quietly through deep space for decades. The technology development cost is not trivial. The trajectory is more conventional in shape, but it does not deliver the same outbound speeds without unusual reactor and thruster assumptions. Hybrid architectures, in which both ideas contribute, are the third lane in the same trade space. A hybrid mission might use a near-Sun trajectory and a partial sail for the initial high acceleration phase, then deploy or rely on an electric propulsion stage for the long cruise to maintain or build speed. The 2026 paper describes this kind of architecture as the most plausible route to the lower end of the 20-year transfer goal. A hybrid is plausible only if several hard requirements hold at once. The initial injection has to be strong, which means a real perihelion pass and a real sail or solar electric stage. The cruise stage has to be efficient, which means a working space-rated reactor and an efficient electric thruster, both designed for long operating lifetimes. The combined system has to survive both the hot perihelion phase and the very cold deep space cruise. The science payload has to remain functional after both stress environments. None of these requirements are unique to a hybrid mission. The hybrid asks for them simultaneously. That is why the propulsion paper does not declare a winner. It explores the trade space and identifies which assumptions each candidate architecture depends on. It treats the sail only, NAP only, and hybrid routes as three different ways of stacking similar difficulties in different orders. None of them is impossible in principle. None of them is comfortable in practice. Each of them buys progress in one direction by accepting heavier engineering risk in another. The honest summary is that the propulsion problem is not a technicality to be optimized after the optical concept is approved. It is one of the main reasons the mission has not yet been selected for development. The optical claim survives independently of propulsion. The mission case for the optical claim does not. Whichever route is eventually chosen, it will demand a level of propulsion performance that current programs are working toward, but have not yet demonstrated at the relevant scale. So the propulsion wall is not metaphor. It is a quantitative requirement that maps directly back to the lens being used at 650 AU within 20 years. Until at least one of the candidate architectures matures into a flight-ready design, the SGL telescope cannot leave the page. Once one does, the same architecture will define the spacecraft that arrives, the power available for the instrument, and the long-duration systems that the observatory has to live with after it gets there. One more constraint deserves attention. None of these propulsion routes deliver a spacecraft that can easily stop on arrival. A high-speed sail mission ends up cruising outward at tens of AU per year and would continue past the focal region rather than parking inside it. NEPI and hybrid architectures can in principle decelerate, but only by spending propellant they would otherwise use to maintain station. The current concept work treats the focal region as a band the spacecraft drifts through over years of observing, rather than a destination it breaks into. That is consistent with the geometry of the focal line, which extends outward without a sharp far boundary, but it does mean the observing campaign happens during a controlled outbound drift rather than in stable orbit. The metrology and station-keeping requirements take that drift into account. At 650 astronomical units, a radio command does not arrive a few minutes later. The distance is about 97 billion kilometers. Even at the speed of light, a one-way signal from Earth takes roughly 90 hours to reach the spacecraft. A round-trip exchange, in which Earth sends a command and the spacecraft sends back an acknowledgement, takes about 180 hours, that is 7.5 days, for a single full exchange. This number is not a quoted mission specification. It is simply the consequence of the distance, and it follows directly from the constancy of the speed of light. The 2026 Propulsion Trades paper assumes mission distances in the 650 to 900 AU band. The 2020 mission paper assumes the same kind of observing geometry. The one-way light time falls out of those assumptions without any further engineering input. The operational consequence is large. A spacecraft inside the orbit of Mars can be flown in something close to conversation. The round-trip time is on the order of tens of minutes. Operators can send a command, observe the spacecraft's behavior, and send a correction within the same shift. A spacecraft at the heliopause is already too far away for that style of operation, but the round trip is still measured in days. A spacecraft at 650 AU is in a different regime entirely. By the time a problem on the spacecraft has been reported to Earth, analyzed and answered, more than a week has passed. A solar gravitational lens mission spends a substantial fraction of its observing campaign in the middle of a scan across the image plane. The scan involves repeated, precise movements of about 10 meters at a time, with measurements taken at each position, in a controlled sequence designed to support the inversion. During those movements, the spacecraft cannot wait for Earth to confirm each step. It has to act on its own. This is what autonomy means in context. It is not a futuristic feature of the spacecraft. It is the operational mode the distance forces on the mission. The spacecraft has to make routine decisions about scan progress, calibration, drift correction, and instrument health entirely on board. Earth's role becomes setting the overall plan, monitoring the data that arrives much later, and intervening only at strategic points where the round-trip delay is acceptable. That changes the design of the spacecraft and its software. The instrument has to come with on-board models of the lens, the corona, and its own state. It has to be able to detect problems with its measurements while they are happening, not days after the fact. It has to keep its own log of what it has done and why, in enough detail that Earth can audit the campaign weeks or months later. None of this is impossible. It is a real engineering program, and one that is not yet completed in published form for a flown deep space mission of this kind. There is a separate question about staying healthy at all. The spacecraft at 650 AU is also a long way from the Sun's electrical power. Sunlight at that distance is more than 400,000 times fainter than at Earth. Solar arrays are not an option. The spacecraft has to rely on radioisotope power systems, or on the same small nuclear reactor that may also be providing propulsion. Both routes have long histories in deep space missions, but neither is generous with power. A 1-meter optical telescope, an active coronagraph, a detector, an onboard inversion pipeline of some kind, propulsion for fine corrections, and a communication system all have to fit inside a power budget that is more constrained than anything operated at planetary distances. Long-duration systems matter as well. A mission whose transfer is 20 years, and whose observing campaign may be several more years, has to keep its electronics, its thermal control, its thrusters, its detectors, and its communications all in working order for decades. Components have to be designed for very long lives. Subsystems have to survive both the hot perihelion phase, if the propulsion choice required one, and the very cold deep space cruise. Failure modes that would be tolerable on a 5-year mission become serious on a 25 or 30-year one. The mission has very little margin for component replacement because there is no plausible servicing visit at 650 AU. The 2020 mission paper and the 2026 Propulsion Trades paper both treat these constraints as part of the design, even though neither claims to have resolved them. Power, autonomy, and long-duration reliability appear in the trade space alongside propulsion and instrument capability. They do not have neat closure. They are real, ongoing engineering challenges that the proposed mission has to clear before it can become more than a paper concept. So the picture at this point is consistent. The spacecraft has been delivered to the focal region. It has the right optics in front of it. It has, in principle, the right detector behind those optics. It is now living in an operating environment that is unlike anything previously flown. The distance has stretched its command loops to a week. The power available to it is small. The systems that keep it functioning have to last for decades. And the science it is doing depends on its ability to make careful decisions on its own, in the middle of a measurement campaign that Earth cannot supervise in real time. In short, the spacecraft has to behave more like a slow, careful remote scientific operator than like a typical deep space probe. Telemetry and commanding remain the same kind of activity they have always been, but the cadence is different. The instrument has to be smart enough to be left alone for long stretches. The mission has to be patient enough to plan in those stretches. None of that is exotic in principle. All of it is unfamiliar in practice, because no current mission operates this way at this distance with this kind of science to deliver. The downlink side of this picture is also constrained. At 650 AU, the spacecraft is communicating with the deep space network across roughly 97 billion kilometers. Even with a high-gain antenna and a powerful onboard transmitter, the data rate at that distance is small by terrestrial standards. The spacecraft cannot afford to send back raw data for every sample of the image plane. It has to either compress its measurements on board or pre-process them into intermediate forms that fit the available bandwidth. The 2026 benchmark assumes a data handling pipeline that lives partly on the spacecraft and partly on the ground. The exact split has not been finalized in public work, but the constraint that the link is the bottleneck is clear in every concept paper. That is the operating environment the proposal has to inhabit. It is the same environment in which the spacecraft has to stay precisely on its observing corridor while the campaign runs. Without that ability to stay on the corridor, the autonomy and the power and the long-duration systems are supporting an instrument that is no longer producing usable data. A spacecraft that holds position on a line is doing more than staying still. The line, in this case, is the focal corridor of the solar gravitational lens for a specific target star. The spacecraft is moving outward along that line during its observing campaign and sampling the image plane as it goes. To do the imaging that the proposal cares about, the spacecraft has to remain on the corridor with enough precision that each sample lands where the Reconstruction expects it. This is not the same problem as keeping a satellite at a Lagrange point. A Lagrange point is a place where gravity and orbital dynamics conspire to keep an object roughly stationary relative to two larger bodies. A solar gravitational lens corridor is a long, straight line in deep space that has nothing equivalent. There is no local minimum of potential to settle into. There is no orbital mechanics that quietly holds the spacecraft in place. The spacecraft has to assert its position actively, using its own propulsion and its own sense of where it is. The 2022 resolved imaging paper from Turyshev and Toth and the 2026 observability benchmark both treat alignment as a scientific requirement rather than as a navigation convenience. The line geometry connects the target star, the center of the Sun, and the spacecraft. If the spacecraft is on the line, the lensed light arrives in the configuration the inversion expects. If the spacecraft is off the line by tens or hundreds of meters, the lensed light arrives differently, and the inversion's assumptions stop matching the physical situation. So alignment is not a flight control add-on. It is part of how the lens works for the spacecraft. The same instrument that records the Einstein ring also needs to know, at each moment, where it stands on the corridor. The 2026 paper lists image plane metrology and navigation error as dominant requirements precisely because mistakes in either degrade the recovered image directly, no matter how clean the detector electronics are. This is the second time the spacecraft's position has been treated as a scientific quantity rather than a flight engineering one. The first time was during the scan across the image plane, where the relative spacing between samples had to be known to about a fraction of the step size. The second time is now at the level of the corridor itself, where the spacecraft has to maintain its place on a line that runs outward through deep space for hundreds of AU. The way to keep that place is through small, controlled corrections applied over long periods. There is no big burn that puts the spacecraft on the line forever. Solar pressure, interplanetary forces, and the slow geometric drift of the target all act on the spacecraft's trajectory. Small position errors can accumulate into large ones over months and years. The mission has to budget propulsion, attitude control, and metrology for sustained operations rather than dramatic course changes. This is what station keeping looks like in this context. It is not a single heroic effort. It is a routine, repeated activity built into the way the spacecraft operates. Each correction is small. Each correction is made on the basis of the spacecraft's own measurement of its position, with reference to onboard inertial systems, star trackers, optical references to the Sun and to nearby planets, and any other navigation sources that can be carried that far from Earth. The 2026 benchmark assumes that this kind of continuous metrology is present in the mission design, because the modeled imaging case depends on it. The other half of staying on the line is metrology in the optical sense. The instrument has to know, beyond the corridor geometry, where it is sitting in the image plane of the lens. That image plane is defined by the optical relationship of the Sun, the target, and the spacecraft. As the spacecraft moves outward along the corridor, the image plane moves with it. Mapping the spacecraft's physical position onto its image plane position requires careful calibration of the optical system and careful logging of measurements over time. The data has to be self-consistent for the inversion to work. Across a long observing campaign, this becomes a sustained discipline. Calibration runs have to be scheduled into the science timeline. Reference observations have to be made at known points to anchor the system's behavior. Drift, when it appears, has to be characterized and removed before it can corrupt the recovered image. None of this is glamorous. All of it is necessary, because the science depends on a long chain of careful measurements being interpretable as a single coherent dataset. A useful side effect is that the same metrology effort improves the spacecraft's tolerance to other small problems. A slight detector drift, if it is well measured, can be calibrated away. A small mismatch between the spacecraft's onboard model of its position and the actual geometry can be corrected if the metrology is fine enough to spot it. The discipline that keeps the spacecraft on its corridor is the same discipline that keeps the data trustworthy. There are practical engineering questions about what kind of metrology fits in a deep space spacecraft. Laser interferometers used in ground-based gravitational wave observatories operate at micron precision over kilometer baselines. Scaling that down to a single spacecraft requires more compact optics, but the underlying physics is well understood. Star trackers, used routinely on existing missions, can give attitude precision at the arcsecond level. A combination of star trackers, an inertial measurement unit, and onboard reference observations of solar system objects can in principle pin down both attitude and position to the precision the 2026 benchmark assumes. None of these instruments are exotic. Putting them all on one spacecraft and operating them for 2 decades at 650 AU is a different kind of challenge from any of the individual technologies. The cost of all this is observing cadence. A spacecraft that has to keep its corridor, hold its image plane metrology, and run calibration runs alongside its science measurements is not free to do other things. Its observing time per target is set by the inversion's requirements and by the speed at which the spacecraft can step across the image plane. There is no leftover capacity for casual exploration. The campaign is built around one corridor, one target, and one carefully planned scan. That is one reason the 2020 mission paper and the 2026 propulsion trades paper treat a first SGL mission as a campaign instrument rather than as a general observatory. The mission's strength is in producing a high-quality reconstruction of one target. Its weakness, by the same physics, is that it cannot easily produce many such reconstructions. The corridor and alignment discipline that buys the science also defines the limit of how much science any single mission can do, so holding the line is part of how the telescope works. Without it, the spacecraft is collecting noise that the inversion cannot interpret. With it, the spacecraft is supplying the inversion with a long series of disciplined samples that can in principle recover a planet. The next question is what the choice of corridor implies for the kind of science the mission can deliver overall. Most exoplanet surveys can choose what to look at after the instrument is built. A space telescope with a wide field of view and flexible pointing can be assigned targets year after year, sometimes by changing observing programs between funding cycles. The science instrument and the science targets are largely independent. A solar gravitational lens mission does not work that way. The instrument is the spacecraft, the optical system is the Sun, and the connection between the two is the corridor that runs from the target star through the Sun's center and outward into deep space. The corridor is fixed once the target is chosen. The spacecraft is committed to that corridor for the full transfer to 650 AU or beyond, and for the duration of the observing campaign that follows. This is why target selection is not a downstream decision. It is part of the mission design. The spacecraft has to be aimed at the line behind the Sun for a specific star long before launch. Once it has been launched, its destination is set. Its science targets are not chosen by an observing committee after the instrument arrives. They are chosen by whichever line the spacecraft is on. That has a sharpening effect on the candidate list. A useful SGL target is not just an interesting planet. It is an interesting planet whose host star has a geometry that puts a focal corridor in a location a mission can reach, on a timeline that closes inside 20 years, with a propulsion architecture that can be built. The 2020 mission paper and the 2026 propulsion trades paper both treat this kind of selection as the central exercise in mission planning, rather than as a soft optimization layer. For an Earth-like target, the candidate set begins with the same nearby star systems that other direct imaging missions look at. Proxima Centauri, the nearest star, has at least one known planet in its habitable zone. Several other nearby Sun-like stars have planets that are interesting for habitability studies. The closer the target system, the brighter the lensed signal at the focal region, and the more comfortable the operating budget. Distance to the target system matters partly for the same reason any astronomy mission cares about distance, and partly because the geometry of the corridor is shaped by where the target sits behind the Sun from Earth's reference. The current literature is careful not to overcommit to a specific target. It treats the SGL as a flexible concept with a small set of candidate worlds, but it does not declare which one will be chosen if a mission is funded. The target choice depends on the state of detection programs by the time the SGL mission becomes selectable. It also depends on whether the survey instruments that come before, like the Habitable Worlds Observatory or its successors, identify a particular nearby planet whose properties are striking enough to justify the SGL effort. So the practical question is not just where to send the spacecraft. It is what kind of planet would be worth the commitment. A small number of candidate worlds, identified by survey work, would form the input to that decision. The SGL is then a finishing instrument for one of them, not a general survey of all of them. This is what it means to call the SGL mission a campaign instrument. It is built to do one large, careful piece of imaging of one well-chosen world with a very long preparation. It is not built to hop between targets in the way a conventional telescope hops between fields. The mission's value depends on the quality of that one campaign, on the careful selection that preceded it, and on whether the eventual reconstruction is informative enough to justify the cost. Now imagine that the SGL mission has completed its first target. The spacecraft is sitting somewhere in the 650 to 900 AU band on a corridor pointed at one particular star, with several years of detailed reconstruction work behind it. There is a temptation to ask what comes next. A second target would mean leaving the current corridor and reaching a different one, several hundred AU off in another direction. The geometry of the focal region does not allow a small pivot. A new target means a meaningful change of position in three-dimensional space, far from any reasonable source of propellant or power. The 2020 mission paper, the 2022 resolved imaging paper, and the 2026 propulsion trades paper all treat retargeting as a hard constraint rather than a routine option. They do not declare that retargeting is impossible. They do say that it is structurally different from repointing an ordinary telescope. A retargeting maneuver is closer to a second mission than to a maintenance burn. It uses propellant, time, and operational margin in the same league as the original transfer to 650 AU. For the same kind of architecture, retargeting could easily mean adding a decade or more to the spacecraft's working life, with no guarantee that the systems can survive it. That has consequences for how the mission's eventual science is described. A successful SGL mission, in the current published treatment, produces a high-quality reconstruction of one Earth-like world and a smaller amount of supporting data. It is not in a position to deliver a comparative survey of several such worlds. The single-target nature of the mission is therefore not a limitation of one design. It is a structural property of the geometry the Sun's gravitational lens forces on any user. This is the right place to keep the proposal honest. The optical promise of the SGL is unique in current astronomy because it offers resolved imaging of an Earth-like planet where nothing else does. The mission cost of that promise is just as unique because it demands a single corridor commitment that cannot easily be shared across multiple targets. A funding decision in favor of an SGL mission is in effect a decision to buy resolved imaging of one specific world at the price of a very long, very specialized deep space project, that is a defensible choice. It is also a different kind of choice than is usual in space astronomy, where instruments are normally judged on how broadly they can serve a research community. The SGL serves one carefully chosen target very well, or none at all. There is no middle path within a single mission's lifetime. A small set of secondary observations may be possible. The same spacecraft, sitting at a few hundred AU, has a vantage point on the rest of the solar system that no current mission shares. It could carry instruments to study the heliosphere from outside, to measure the interstellar medium directly, or to do precision tests of general relativity using the Sun as a probe. Several SGL mission concepts include such secondary science as a way to make the spacecraft useful during cruise and after the primary imaging campaign. Those measurements would not in themselves justify the cost of the mission. They would extend its scientific value once the spacecraft was already at the relevant distance. The 2020 mission paper notes that secondary science is possible, but does not let it dominate the design. The optical imaging objective remains the reason the mission has its propulsion architecture, its observing distance, its alignment requirements, and its long-duration systems. Any secondary use is a bonus rather than a driver. That ordering is important. A mission that traded its primary imaging configuration for better heliospheric science would no longer be an SGL mission. It would be a different deep space project that happened to be passing through the right region. So the answer to what the spacecraft can really observe, given everything that has come before, is narrow but specific. It can observe one chosen Earth-like world at much finer detail than any planned alternative. It cannot easily observe a second world without effectively becoming a second mission. The science return is bounded by that choice. The justification for the mission has to be willing to accept that boundary as the cost of an otherwise unobtainable result. By now, the optical claim has held up. The mission claim has not closed. Both halves of the answer are needed to say anything useful about whether the Sun can become a telescope. The optical claim is direct. The Sun is massive enough to bend the light of a distant planet into an Einstein ring on the far side of the focal region. The amplification is around 10 to the 11th at visible and near-infrared wavelengths. The angular reach is fine enough to support resolved imaging of an Earth-sized planet at a few parsecs. The 2018, 2020, 2022, 2025, and 2026 papers from Turyshev and collaborators do not retreat from any of this. They sharpen it. They show how a small telescope sitting in the right place can in principle collect enough light from the ring to support a long-duration imaging campaign. The 2026 observability benchmark establishes that the recovery is mathematically tractable under stated assumptions, with a modeled image cylinder about 1.34 kilometers across and a sampling pitch of about 10 meters for a 128 by 128 reconstruction. That is the strong yes. The Sun can act as a real lens for an Earth-like exoplanet. The proposal is not metaphor and not fantasy. It is a concrete optical claim resting on continuous published work that has not been refuted by competing analysis. As a research lane, it is alive, and as a candidate physical instrument, it remains the only known route to resolved imaging of another Earth using equipment that humans could in principle build at the current frontier. It is worth being precise about what this yes does and does not include. It does include the geometry, the photon budget, the amplification, and the in-principle reconstruction. It does not include a flown spacecraft, a delivered image, or a funded mission. The optical reality of the lens does not depend on whether anyone ever uses it. The science result, the thing that would let anyone say a planet has actually been imaged, depends on much more than the optics, so the yes is real, and the yes is narrow. It belongs to physics rather than to engineering. It justifies treating the SGL as a serious candidate concept on every list of future telescope ideas. It does not justify treating the SGL as something close to being built. The condition is the other half of the same sentence. The mission case for the SGL has at least 4 hard constraints that are independently capable of breaking it. The first is distance. The lens does not begin to work until about 550 AU, and the practical observing band sits farther out around 650 to 900 AU. That distance is operational, not just geometric. It sets a 20-year cruise as a target with no comfortable propulsion architecture, and turns the question of building the telescope into a question of also building a deep space mission unlike any flown before. The second is noise. The sun that bends the light also fills the field with a structured, time-varying corona that the spacecraft has to look past. A coronagraph helps, but it does not remove the problem. The recovery of a planet image depends on careful, sustained calibration of coronal contamination as part of the same dataset that carries the lensed signal. The third is reconstruction. The Einstein ring is not the image. The image comes out of a long observing campaign of disciplined sampling, fed into an inversion that uses a model of the lens, the corona, the detector, the spacecraft's positions, and the planet's own time dependence. The modeled benchmarks suggest the inversion works for the kind of target the proposal cares about. They do not yet replace an end-to-end demonstration on real data, which by definition has to wait for a real mission. The fourth is alignment and operations. The spacecraft has to remain on a narrow corridor in deep space, step through its image plane with meter-scale precision and known position, perform calibration and station keeping continuously, operate autonomously across a 90-hour one-way light time, survive on radioisotope or small reactor power, and keep its long-duration systems healthy for 2 to 3 decades. Each of these requirements is real engineering work. None has been fully demonstrated for a mission of the relevant kind. Any one of these 4 constraints, if it cannot be resolved, blocks the SGL from becoming a working telescope. A distance can defeat the mission by making the schedule impossible. Noise can defeat it by leaving the recovered image dominated by coronal artifacts. Reconstruction can defeat it by failing to produce a faithful planet estimate from real data. Alignment and operations can defeat it by corrupting the data the spacecraft is collecting in the first place. The optical claim survives all of these, but the mission does not necessarily survive any of them. That is the adult answer. The sun can become a telescope in principle. Whether it becomes one in practice depends on whether a specific deep space mission with very specific propulsion, alignment, autonomy, and noise handling capabilities can be built, launched, operated, and trusted. The yes belongs to general relativity. The condition belongs to spaceflight engineering. Both halves are honest. Neither half should be left out. This is also the reason the SGL stays on serious lists despite the condition. The competing proposals do not, at present, offer a resolved image of an Earth-like exoplanet on any plausible schedule. The SGL does, on paper, with the proviso that the mission burden has to be carried. The choice is not between an easy alternative and a hard one. It is between accepting the mission burden of an SGL mission and accepting that resolved imaging of another Earth remains out of reach for a long time. That is not a comforting choice. It is the actual state of the field. So when the original question comes back, the answer can be stated cleanly. The sun can become a telescope. The telescope already exists as an optical configuration in the focal region beyond 550 AU. What does not yet exist is the mission to use it. Until that mission is built, the lens remains a real instrument with no users. Once that mission is built, if it is, the same lens will become a working telescope for one carefully chosen world, at the price of one of the most demanding deep space projects humans have ever attempted. That is the answer the rest of the case has been leading toward. It is not a single yes. It is not a single no. It is a yes about physics and a not yet about engineering, and the gap between them is what defines the rest of the work. There is one more thing worth saying about how the mission case is likely to evolve. The 2018 paper established the optical case. The 2020 paper added the mission concept. The 2022 paper deepened the resolved imaging analysis. The 2025 paper compared the SGL with the alternatives. The 2026 papers added the observability benchmark and the propulsion trades framework. None of these papers ends with a triumphal claim that the case is closed. Each one identifies a specific question for the next paper to address. That kind of progression is how serious mission concepts mature, and it is also how they sometimes fail. A concept that runs out of well-posed next questions, or that turns out to have a hidden requirement that no architecture can meet, can quietly drop off the list even after a decade of work. The SGL is not in that state, but it is also not at the end of its development. It is somewhere in the middle, with the case clearer than it was in 2018, and the open questions sharper than they were then. The starting picture stays. A small spacecraft is sitting on a specific line in deep space, several hundred AU from the Sun, with a 1-meter telescope pointed back at the solar disk. A faint Einstein ring of light from a distant planet sits around the Sun in the spacecraft's view. The ring is real. The lens is real. The optical configuration is the one the proposal needs. What changes is the meaning of that picture once the rest of the case is in view. The ring is not the photograph. It is a mixed optical signature that has to be sampled, cleaned, and reconstructed. The line is not a destination. It is a corridor the spacecraft has to hold and step along for years. The 1-meter telescope is not a small upgrade to an existing observatory. It is the detector behind an instrument whose aperture is the Sun. The optical promise is large enough to explain why the proposal still matters. The amplification is around 10 to the 11th. The angular resolution is around 10 to the minus 10 arcseconds. A modeled Earth-like world at 30 parsecs gives an image cylinder about 1.34 kilometers wide, with sample spacing of about 10 meters for a 128 by 128 recovery. Those numbers are why the idea survives comparison with ordinary telescope paths. The cost is just as physical. The mission has to reach 650 AU in something like 20 years, which points toward an average outbound radial speed near 154 kilometers per second. It has to operate under a one-way light time of about 90 hours. It has to look through the solar corona, keep its own position known, and turn a long scan into an image whose limits are honestly understood. None of those tasks is decorative support work around the telescope. Each one decides whether the ring data still means what the reconstruction assumes it means. That is why the mature answer cannot stop at the lens. If the spacecraft arrives too slowly, the telescope may be too late to justify. If the power system fades, the observing campaign can stop before the image is earned. If the corona model is wrong, the planet signal can be buried in the Sun's own light. If the scan position is poorly known, the image plane becomes a bad map. If the spacecraft cannot correct itself during the campaign, Earth is too far away to rescue each step in time. So the answer is narrow, but it is not small. The Sun can become a telescope in the strict optical sense. The lens exists. The reconstruction is conditional but plausible. The mission wall is real, and it decides whether that lens ever becomes a working observatory rather than an unused instrument waiting in the geometry. For now, the Sun keeps bending the light. The focal line is still out there, beyond 550 AU, with the practical observing work farther still, along one narrow corridor. Whether a spacecraft ever reaches it is a mission question. Whether the lens is real, powerful, and at the right scale for this kind of imaging is no longer the uncertain part.